right, guys. Sorry, some of this is already done. This is like my second go around. Not bad. But today we are going to finally do our very first proof. And we're going to kind of do sort of simpler proofs. We're going to prove some things that you're a little bit more familiar with and a little bit more comfortable with, rather than jumping into geometric proofs. Now, if we're lucky and if you guys are really into proofs, we can do more later, but this is kind of where we might leave proofs for this year. We'll see. Okay, so on 20 and 21, we're going to add our algebraic proofs, but I do want to just add in the rest of the proofs that I gave you guys and put them in our notebook, and they'll be blank for now, but we might come back to them later. So the next one we would have is geometric proofs on 22 and 23, segment and angle proofs on 24 and 25, and then finally parallel line proofs on 26. So if you need to take a pause and write all that down, it's kind of a lot. I'm going to turn. So here's where we might have to figure some things out. On 20 and 21, I'm going to leave 20 blank. 21 just gets folded in half like a little mini book, where this is our cover. That's on the inside. Again, sorry, I already did this. On 22, we would leave that blank. And then on 23, this should be the next one that you have in there. And you're going to want to flip it over and fold it in half like a backwards book. Get that taped in there. And then on 24, 25, we had our segment and angle proofs. And these are the next two in your note packet. And those should both just get folded in half like a book. So we have our segment addition stuff, and then our angle addition stuff. Look at all those words. Like, aren't you so happy we're maybe not doing this? I don't know. It could be a lot of fun though. I do love proofs. I can really nerd out. So that's on 25. And then lastly, on page 26, this should be the last page that you have in your notes packet, and it's proving parallel lines. So fold that in half like a book, and that can go on 26. Now, don't feel like, you're going to be super behind if we don't do these proofs. Honestly, you will never see proofs again unless you want to be super cool like me and go to college to get a math major. It is a lot of fun, but they will go over all this stuff again with you then. So it's just a nice little base foundational proof stuff. Okay, so after all that, let's actually go back to page 20 and 21. And I actually want to start with you on page 20 because there are different ways to go about proving something. There are different types of proofs that we can do. So that's what I want to write with you here. So types of proofs. Now, one type of proof that is kind of fun to do, and hopefully we'll get to try when we come back, is a proof by construction. Now, anymore, if a mathematician is going to do a proof by construction, usually they would use a software on their computer to construct different figures, like a line or an angle or a triangle or something like that, to try to prove something. We'll hopefully be able to get to try a proof by construction later when we get talking about triangles. Another type of proof that you can do them by hand too. You don't have to use software, but the way we would do it by hand is you would use like a ruler or a compass or a protractor. So the protractor is how we measure our angles. A compass is the fun thing that makes circles all the time. So we'd have to use our math tools of destruction to do that. Another type of proof, again, that I would like to maybe try with you guys later on when we're talking more about triangles, is a flowchart proof. You guys maybe do flowcharts in English when you're charting out a story or something. I don't know, maybe I'm making that up, but a flowchart proof is just kind of like you have this thing that leads to this thing. And like that's literally what we do in math as well. So flowchart proof, I think, can be really fun. Another way to prove something, and to be honest, when I was in high school, the way that my math teacher made us prove everything was with a paragraph proof. And honestly, I would love to say you guys should do that as well, because for me, it really helped to make sense of everything. Essentially, a paragraph proof is just using the law of syllogism over and over and over again. So a bunch of if-then statements connected together to finally come to your conclusion. So that's a paragraph proof. And the last way that we have, and actually I never learned how to do this until I was a teacher, and that's a 2-column proof. And so it was a little bit hard for me to figure out how a 2-column proof worked, but now after doing it for so long, I think it is sort of the most straightforward way to do a proof. Also requires the least amount of work, which I know you all love. And so we're really going to focus on our 2-column proof. So when we're doing a 2-column proof, we set up sort of like a T-chart, where on the left-hand side, we put our statements of fact. And then on the right-hand side, we put our reasons for knowing that fact. So whatever I put over here has to be backed up with a reason. We always start our statement off with the hypothesis of our conditional statement. And we can start with that always because it's given to us that that should be true. And then hopefully we can use some other math facts in between to finally come to our conclusion, where we will be able to give some reason for why that is, depending on how we got there. It just depends on the journey. Okay, so if we kind of take a look here, on the front, I know this looks overwhelming. There's a lot of information there, but it's information you already have. We have our addition property of equality, all of our properties of equality that we talked about the other day. So we have our reflexive, symmetric, transitive, new properties, but then our substitution, our distributive property. So these are all just examples over here. It's just more examples for you to look at. Now, we can also talk about those properties, the reflexive, symmetric, and transitive, in terms of angles or segments. But again, that's kind of getting into geometric stuff that I don't know that I want to do with you guys yet. Okay, so let's actually open this up, because on the left-hand side, we have 2 algebraic proofs. On the right-hand side, we have 2 geometric ones that we're just not going to worry about. So it's all good. So the way an algebraic proof works is whatever you are given is your hypothesis, or kind of your math problem. And whatever it is you're trying to prove is the conclusion or the answer. So you already know what X is, but it's really about the journey. Like, how did I get there? What were all the steps in between? Okay, so we have our T-chart already set up, our statements and our reasons, and we'll always first write down our hypothesis, or whatever it is that is given to us. So 3 plus 4, and we don't want to change it in any way. We're just going to write it down exactly. And the reason that I can say this is because it is given to me as fact. So this is given. So then I just have to think about how I'm going to solve that problem. Like, how would I solve that math problem? And I feel like for me, the first thing I would do is the distributive property. And so when I distribute, I will then next have 3 plus 4x minus 8 equals 27. Now again, the reason that I got from here to here was because I did the distributive property. Okay, now I feel like the next thing I'm going to do, if I was solving for x, is I would want to combine like terms. I noticed that I have some like terms over here. I'm going to want to combine them up. So when I do that, I would have 4x minus 5 equals 27. You can already see, I think I'm going to run out of little lineies on here. I don't know what I was thinking, but that's fine. So what I did from here to here, now this is kind of strange because I technically, I guess, added or subtracted, but I didn't do it on both sides. So it's not that property of equality thing. Truly what we did was we combined like terms. So that's what I'm going to say. Now I know, again, that's not a reason that we talked about, but that is a math fact. Terms that are alike, you should combine. That's understood as math fact. But now, continuing solving for x, so going back here, I feel like what I would do next is add 5 on both sides. And I don't normally like to write out my steps like this, but I feel like on this first one I'm going to. So I'd add 5 to both sides. And so my next statement would look like 4x equals 32. Sorry. So because I added 5 on both sides, my reason for being able to go from here to here was the addition property of equality. And so then continuing solving for x, I think the next thing that I would do is I would divide 4 on both sides. And once I do that, my next statement will look like x equals 8. Again, kind of went out of the box, sorry. And yeah, I could do that because of the division property of equality. Now, I know that I'm done because I've solved my math problem. I also know that I'm done because that's what they wanted me to prove. They wanted me to prove that x is equal to 8, and I've done that. So my proof is complete. My gosh, don't you love it? Let's try another. So guys, I tried to use color here because the one weird thing that I will admit about 2-column proofs is that kind of whatever you do here is what I write over here. And then I have a new one. And so then whatever I do here, I write here, and then I have a new statement. And then whatever I do here, I write here, and I have a new statement. So it's kind of weird. It feels like you're always kind of a step behind. I think I'm going to do it with color again. Okay, so on this next one, I'm going to always write down first what is given to me. And my math problem that is given to me is 2 parentheses x plus 2 equals, I'm going to change that to half, x plus 1. And I can write that down because the math gods say it was so, and it is given. Alrighty. So then I want to go about my business and eventually prove that x is -2, and I sure hope that it is. We're going to find out by using our math facts of algebra. And so I feel like the first thing I would do, again, is over here. I would do the distributive property. So I'm going to distribute, and this is what I sometimes find easier to do too, is I write down what I'm going to do, and then I go do it. So 2x plus 4 equals half x plus 1. And then, you guys are good at math. You can handle this. Because I think I'm going to do the next thing, but I'm going to do it twice. So I want my x's to be together, and I'm going to have to subtract the half x both sides. And I want to subtract that one because it's smaller. But at the same time, I also don't want this 4 over here with the x. So I'm going to subtract 4 both sides. Now, I feel like I can do that all in one step, mainly because you guys are good at math, and because I'm doing subtraction all around. Now, if I had to subtract the x's, but then like add the other numbers, I think I would do that in different steps because it's not the same property of equality. But since I'm straight up subtracting, we could do the subtraction property of equality here, and I feel that that would be fine. And again, if we added x's and then added non-x's, we could use addition property of equality all in one as well. Okay, so when I do that, I'm going to have, so 2 minus half is, but wait, oh my gosh, I almost did half. 1 1/2, which is 3 over 2. Sorry, I know you hate it. 0 equals -3, like that. So I fully simplified. So then the next thing I would do to solve for x is I would multiply both sides by the reciprocal. So I know normally when we have multiplication, we divide, but I'm not dividing in this case because they're fractions. I am multiplying by the reciprocal. So we have our multiplication property of equality. Multiplying both sides by 2 over 3, reciprocal of 3 over 2. So then x is alone, and then -3 times 2 over 3, the 3's can divide out, so it's just -2. Oh my word, we're done. I had way more lines here than I needed. So again, these are probably like just a guideline. I don't know. Maybe I meant to flip those. I don't know. Let's try another. Go back over to page 20 and we will try another one. Slightly more interesting. I want to do this one. So let's say that it is given that 3/4 z minus 2 equals -5. And we want to prove that -4 equals z. I should have not used a z because sometimes they look like 2's. Oops. Halfway through, we're going to end up changing it to an x anyways. So I'm going to put in my 2-column proof. Over on this side, we're going to have statements. Over here, we're going to have reasons. And the first statement that I always put is what's given to me. So 3/4 z minus 2 equals -5. And I can write that because it's given. Now, I would really prefer in our proofs if we don't have to show all of our steps, if we don't have to show all of our work. So I think the next thing that we would do to solve for z, because that's what we're trying to do is get z alone, is I would add 2 on both sides. So we're doing the addition property of equality. And I'm just going to do it. So 3/4 z, and when I add 2 here, we're at -3. The next thing I would do to get z alone is I would multiply by the reciprocal again. So I'm going to write down multiplication, property of equality. Sorry, it just sounded out. Me too. And when I do that, when I multiply by the reciprocal, we're going to end up with z equals -4. And it feels like you're done, but you're not done. This is where I know it can get really nitpicky. But that is not exactly what I have here. And like, it seems so silly that I need to rewrite it one more time, but I truly do. I need whatever I'm trying to prove to look identical to whatever I end up with. And so I do need to reverse it, but that's okay, we can. If I reverse the order of something like that, or I flip it around, we have a property that allows us to do that, and that is our symmetric property of equality. So kind of getting a little new property up in there. Gotta love it. Now guys, I should say, doing algebraic proofs like this, I think is super easy and fun because we're just solving for x, but truly what we use proofs for in math is to prove our conjectures or our conditional statements to be true. And if you are able to do that, then they are no longer conjectures anymore. They're called theorems. So essentially, I've proven the theorem, if 3/4 z minus 2 is equal to -5, then z will equal -4, or truly -4 will equal z. So I've proved that theorem to be true. Now we'll deal with theorems a lot in geometry. And to know that they're actually true, I should go through and prove them. But they're theorems because somebody else already did prove that they were always true. So that's cool. Anyways, good luck. Let me know if you have questions. I think this is hopefully easy.